About polymer knots. Christian's first two lectures were about network structures. Now, of course, topology plays an important role in networks, and it's frozen in a certain way, namely by these cross-linkers, right? So, another way that topology can be frozen in is by just taking a single strand and closing it on itself. And that way you form a knot, which we heard quite a few things about this morning. Before I discuss that in more detail, so I've got two pictures of experiments which I don't understand, where people look at knotted states in DNA. Now, as Jean-Francois discussed last week, the important feature in a cell where there's really extremely long strands of DNA present is that it's compressed into a very, very small volume. Obviously that means long strands, little space to move in, so knotted structures really frequently arise inside biological systems. But as you heard this morning, I mean, knots crop up in a lot of different places as well. So, I mean, people can sort of synthetically produce molecular knots. People can even make knots in light. William Irvine's lecture, knots appearing in fluids. So these structures appear in many places. For us, the relevant thing is that if you have a polymer system in which you have a knot, then this topology affects the dynamical and static properties of this polymer system. So Christian discussed in his lectures how, for instance, elastic properties or forces of networks are affected by the fact that you induce sort of permanent freezing of the topology with cross-linkers. The same thing holds for polymer knots as well. So that's what I'll be discussing a bit later today. Before we get to that, for our intents and purposes, if I say a knot, what I mean is some projection of a three-dimensional knot onto a two-dimensional surface. So this is courtesy of Wikipedia, the sort of standard table of the first few prime knots. What are prime knots? Prime knots are knots that have the minimal number of crossings that they could possibly have. So you can see that they're ordered according to the number of crossings that they have. Obviously one could take such a knot and manipulate it so that it gets more crossings, but if you simplify them, these are sort of the first few simplest knots. Importantly, they're topologically distinct. So for instance, it's pretty obvious that I can't take this knot and change it into that knot without physically breaking a strand. So knots can be classified, and different prime knots are topologically distinct. So now the question, of course, would be, how can I judge whether, if you present me with two knots, whether they're topologically the same object? Are they continuously deformable, one into the other or not? So in this case, like I said, it's obvious that these things are topologically distinct. So this is an interesting question which people have pursued in many ways. One tool that we heard a little bit about this morning is knot invariance. So what is a knot invariant? It's basically a function. You take your knot, plug it in, and you get some result. Alright? So this morning we heard mention of the Jones polynomial. I'm just quickly going to show a brief example on the board of something called a bracket polynomial, which is really the most sort of primitive thing that one can think of. It's not a very useful invariant, but I thought I'd maybe just illustrate these ideas just as an example of a knot invariant. So a bracket polynomial is defined according to three properties. So call them BP1. This one says that the bracket polynomial of the unknot, which we call U, is 1. So the unknot is just simply a simple loop which doesn't have any crossings in it. Okay? So the first rule is, for the bracket polynomial If I take the unknot, I plug it in, I get the answer 1. The second rule for the bracket polynomial is that if I have some product of knot diagram, so some k times u, then the rule that I apply here, I'll discuss this a little bit more in detail just now. So what I should have mentioned, sorry, is that the bracket polynomial is a function where I plug in the knot and I get a polynomial in A. So this is a rule that says if I have an unknot and some other knot k, then I can simplify, or I apply this sort of recursion relation here. So an example of this would be the following structure. So in the middle here I have an unknot, and this is some other part of some other knot. So the bracket polynomial of this, according to the rule above, is simply this prefactor times whatever remains once I've taken the unknot out. So I don't know, is this rule clear? That's what I mean by the product of these two diagrams. If I try to take out the bracket polynomial of these things, I take out the unknot and give it some prefactor here of a to the 2 plus a to the minus 2. Okay, and the last rule then is, as was discussed in the first lecture this morning, some way for how do you splice a given knot. So if you encounter some crossing that would look, for instance, like this, then again you have some kind of recursion relation which gives you a polynomial in A. So here I have some crossing, and this rule gives me a recipe for how do I splice this crossing up. I can splice it up in two ways. I can sort of pull it apart like that, or like that. I do both of those to a given knot diagram, and if I pull them apart this way, I get a factor of A, and if I pull them apart that way, I get a factor of A to the minus 1. So these three things together give you a recursive procedure for, if you start with one of these complicated knots over there, you obviously now have to decompose it until what you're left with in the end is just an unknot. So you literally go about this by splicing every single crossing both ways, this way and that way. And then of course you get products of these diagrams, which you can then split up further and further until in the end you have some polynomial remaining in A. So I mean, I have an example written down here. I don't think it's terribly instructive to actually go through it. Let me just say that this particular knot invariant, so the bracket polynomial, is not a very powerful knot invariant. So what do we mean by powerful? The question is, if I have two knots, let's call them K1 and K2, and these things are topologically equivalent, then a knot invariant has the function of sort of pointing out this equivalent, right? So if I plug in two knots here, they both spit out an answer, then the hope is that this answer should be the same if my two knots are equal to each other, okay? Which is, of course, if I have some complicated knotted structure, it's not necessarily easy to identify this. So that there exist several invariants. I mean, the Jones polynomial or Alexander polynomials, which were mentioned this morning, where this implication works very well. But now the question is, of course, can I make the reverse statement? So if I have two knots, I calculate their invariance and I see that they're equal. Does this necessarily say that the two knots are equal to each other, right? So this is sort of the difference between an if statement and an if and only if statement. The reverse implication is actually the more interesting one because it would give you a tool for classifying knots. It would give you a tool for, I have some machine, I throw in a knot, I get out an answer, and I know exactly to which topological class this knot belongs. So that's what you want. thus far, such a classification scheme does not yet exist. Okay? So up to a certain number of crossings, you get not invariants that really help with classifying things, but beyond a certain point, it's not clear whether one can sort of distinguish all topologically distinct knots. Right. So that's a brief sort of introduction to what knot invariants are. So like I said, currently no complete classification scheme exists. So my talk is supposed to be about polymer knots. Now, why on earth would one consider polymer knots? First answer is, of course, as Christian discussed as well, entanglements just occur in polymer systems. Now, what does an entanglement imply? It implies that I have strands which, simply because they can't move through each other, they freeze in some sort of topological structure. Now, what does one want to do as a sort of statistical physicist? You want to write down a partition function of the system that you're looking at. So, what does a normal partition function look like? It's just the sum over all states of some Boltzmann weight, right? So typically if I have some system, what do I do to find the partition function? I will sum over all states, and each state gets a Boltzmann weight, which is obviously a function of the state. So now what happens if I have some constraint on these states? Christian discussed this a little bit in the context of polymer networks, but suppose that I have some invariant now where I want the invariant of this state, so by state we can say a knot. I want this to have some particular value, I star. So this is an unconstrained partition function, but suppose I want to enforce the constraint that all the states that are summed over have to obey this property. Well, how do you do that? You can incorporate this constraint simply by putting in some delta function. So I'm writing this formally now. Let's just say I of the state must equal I star. So, I hope this notation is reasonably clear. If I don't have a constraint, I just sum over all states. Each state has a certain likelihood of appearing. But now, I want to sum over all states, but select those that have a certain property. How do I do that? I include a delta function formally in my partition function. Right. So, in polymer systems, of course, this is what we do. We write down a partition function, we work out the free energy, these sorts of things. So if I have topological constraints, I want to encode those in some way. I mean, one obvious topological constraint is that strands can't move through each other. But you could also get more complicated constraints, like a knot in a polymer system needs to be conserved. So if I sum over all random walks, I need to select those that obey that knot, or that are topologically equivalent to that knot. So, because this is difficult, people deal with it in effective descriptions. Sorry, can you actually see it with the lights on? Is it clear enough? Or? No. I've got a switch here. I've got a light switch. Ah. So, people sort of try to mimic the effects of this, as Christian discussed as well, by effective descriptions like tube models, where you say, I assume that every strand feels the remaining strands around it by just being confined to a tube of a certain radius. Surprisingly, you can get pretty interesting and useful scaling results from a simple assumption like that. But in simulations, you can do more advanced things. You can, for instance, actually encode not invariants. But doing explicit topological equivalence in a polymer description is very difficult. So, now the question is, if you're a theoretical physicist, how do you maths something like this? Where maths is now a newly defined verb. So, like I said, knot invariants have been reasonably useful in this context because they help you to an extent, sort of distinguish different knots. So here I've written down something terribly hand-wavy with poor notation. So let's look at the equivalent in the context of a path integral. So if I have an unconstrained path integral, what do? I have my measure, and I have some functional dependence in my Hamiltonian on this path. This is an unconstrained path integral. Now what if I want to work out the path integral of a particular knot? Well, again I could say I have some knot, and perhaps I want to capture that this knot has a particular knot invariant. Well, what you can do is then you can, in a functional form, include that the invariant of this path must be equal to the invariant of the particular knot that I'm looking at. So I guess now people on that side can't really see, but I've pretty much written the equivalent statement to that. So here I'm summing over all paths, but I'm selecting only those which obey the same knot invariant as the knot that I am considering. So if I start, for instance, with, let me just quickly go back, this knot 3, 1 there is a trefoil. So if I start with a trefoil, I want to work out its partition function. I sum over all these things, but I select only those which have the same invariant as the trefoil. Now, what are the problems with this? Well, the first one is, this is difficult, right? So path integrals on a good day aren't fun. So now, by putting in some functional constraint, you make it even more difficult. How do people deal with this? They take this functional delta function, and then you can introduce an auxiliary field, put it in the exponential, rearrange things, and if you're lucky, you can integrate out certain things, and then you're left with something that you can actually do. And what does that mean? Well, it would have to be Gaussian in some way, hopefully, because then you can deal with it. But this is very difficult. The other problem is, like we said, knot invariants don't completely classify all knots. So even if you could do this for a given invariant, it's not necessarily very strong or useful. Okay. So there's a bunch of references of people who've looked at this, particularly this paper co-authored by Kolodenko, which it's quite a hairy article, but contains a really nice overview of these ideas. So what we thought about in our work was to take a slightly different approach. So I guess for now I can switch off the lights again. So instead of considering different knots and classifying them with invariants, we rather ask the question, if I have two knots, can I deform one into the other, yes or no? Which kind of addresses the same topic, but in a different way, because it's not taking a knot, putting it into that box, taking a knot, putting it into that box. Is it the same box, yes or no? That's not what we're doing. We're taking a knot, we're trying to manipulate it and then see, can I get it to look like another knot? How do you do this? Well, there are formal rules called the Reidemeister move, which is not some kind of dance. It is in fact formal manipulations on a knot diagram. Now, in the work that I did with Christian in my PhD time, we applied this to two different sort of scenarios. The first one was an equilibrium description, where you really want to find the partition function and then work out free energy and forces and things like that. And the other one was actually trying to encode these rules into a dynamical description. So I'll forget about that for today and focus on the first bit. Before we continue, let's just quickly take a look at these Reidemeister moves. So you recall that table of knot diagrams that I showed you? These are the manipulations that I can perform on those knot diagrams without actually changing the knot. And they're necessary and sufficient, which means this is the only stuff that I can do to a knot diagram without fundamentally changing what knot I'm actually looking at. So the first bit is, obviously, if I have some squiggle on a knot diagram, I can bend it or stretch it or whatever. That doesn't change the topology of the underlying knot. Second bit, if I have some trivial loop like this, obviously I can just twist that strand and the loop disappears. All of this is obviously reversible. Now if I have two strands which lie across each other like this, I can pull them apart. That's also pretty obvious. The last one is just I have a crossing of two strands, and then I have a third strand which I just pull past that crossing. So these are really simple moves, but you can prove formally that this is the only stuff you can do to knot diagrams without changing them. So instead of a clicker question, I will check your awakeness by asking, can I change this knot into that knot? I.e., is there a sequence of these moves that I just showed you, which will take me from there to there and back again? No? So who says no? Who says yes? Aha. So people familiar with knot theory say yes, probably because this is sort of the classic solvable example. The answer is there does exist a sequence of moves. And explicitly, what it looks like is I take this strand, sorry, that one there, introduce a loop into it. Yeah? So this is Reidemeister 1. Then I perform Reidemeister 3, which means I pull a strand past the other one, pull another strand past the other one, then I have a trivial loop over there, I can remove it, and then I just rearrange things, and I'm there. Okay? So this is of course trivial to see. Trivial to see when you look at this. I mean, it's totally obvious, right? Bottom line is, if you look at these two things, there is no a priori way, unless of course you're really good at visualizing this stuff. It's not obvious to me that those two knots are topologically equivalent. They are. Which just means they're related by some sequence of those moves. So I hope that that example sort of illustrates what the point of these Reidemeister moves is, or what they actually tell you. So that was sort of an intro to the tools that we used, and what I'd like to do now is just maybe discuss a little bit what we applied this to. So one of the first problems that people solved with these kinds of path integrals was one where, this was actually Sam Edwards who wrote this paper, I think in 1969. He considered an infinitely long rod and then took a polymer and wound it around this rod and closed it. Alright? Obviously, how do you classify these configurations? Well, one obvious thing that you could look at is the winding number. So you ask yourself, if I wind it around once and I close it, how is this different from winding it around twice and closing it? So here I have my infinitely long rod, take a polymer, wind it around, close it. What do you freeze in? You freeze in the winding number. So the winding number literally just counts how often have I wound this loop around the rod. So how Edwards did this is he physically took the winding number, which you can compute for a certain path R of S around a point, and incorporated it in a constraint in a path integral, and then did some slightly questionable approximations, and ended up with a result for the partition function. So, but bottom line is the winding number is an easy invariant, and already for this it's really quite a rigmarole to actually apply this in a path. So this problem, although it seems really simple, has been addressed again more recently by famous people who are very harsh referees if you should ever get them. So anyway, Grossbeck and Frisch more recently looked at this problem where they then started confining it. Our approach here is a little bit different. What we want to do is also find the partition function, but we're going to go about it in a different way. So suppose you fix the winding number, so you've wound this around W times. Now you can do two things. You can sum over all configurations, like here, and throw out the ones that don't meet your requirements. Right? That's one way of doing it. The other way is you could actually just enumerate all configurations that do obey your requirement. And that's literally what we went and did. So instead of summing over everything and having some function that throws out all the trash, we literally just wanted to actually enumerate all the configurations that are topologically equivalent. So this is a different approach to doing it in the path integral. Let me maybe just try to make that a bit clearer using some pictures. So as you can see, this is your infinitely long rod. So how we now tried to label our configurations was we put some imaginary plane where this rod lies in the plane, and then we considered, here is now my polymer strand that I'm winding around the rod, and we considered the piercings of the plane, right? So here I have R1 and I have R2, and I've labeled these half arcs or half space arcs as TC and TC. What do I mean by TC? I mean that it's an arc that crosses the rod. So if I consider this chain to be an ideal random walk, then I actually know what TC should be. So Chandrasekhar did some really cool work on random walks that are restricted to certain boundaries, reflecting or absorbing or whatever. In that article is the expression for a random walk where you restrict it to a half space, which is exactly what you have here, right? So I've taken R3 and I've cut it in half with this plane. So if I know that this random walk starts on the plane and ends again somewhere on that plane, I know what T is. It's something Gaussian, okay? Right, so I've considered here the case winding number 1, which means I start here, wind it around once, and we see that I can label this with the sequence TC, TC. Pretty obvious. How do you then get a partition function? Well, for this particular configuration, I just need to take these weights, TC, TC, and integrate over the coordinates R1 and R2, because those are literally the only degrees of freedom in this, alright? So what is the appropriate integration domain? This is where it gets a bit difficult, is that this R1 can range anywhere from 0 to plus infinity, whereas R2 can range from 0 to minus infinity, but R2 can never be on this side of the rod. Okay, so this is the sort of singularity in the middle which prevents that coordinate from ever being on this side, and vice versa. So that's why I said the integration domain here, integration domain here is so that the range of integration is restricted to the plus and minus plane respectively. What does the winding number 2 look like? I take the thing, wind it from R1 to R2, wind it back to R3, to R4, and all the way back here. Okay? The corresponding sequence is just 4 of these TCs. So I cross the rod 4 times. How do I work out the partition function of this diagram? I just have to do the integral where these two things must stay on this side of the rod, and those two things must stay on that side of the rod. Okay, so obviously the generalization is winding number W is just TC to the power of 2W, and then integrate over the correct integration domain. But now the question is, if I go back to this scenario, can I still find other piercings of these planes which leave the topology invariant? And the answer is yes. Here's one example. So what I've done here is I've taken this arc that comes back, this TC arc, and after it I've just inserted 2 more arcs, but they stay on the same side of the rod, right? So there's this red bit which I've included. I've labeled them TS and TS for same side of the rod. And so now I have some kind of rule. I can take this basic loop TC, TC, and I can dress it, I can augment it by just adding a TS and a TS. This process is obviously reversible. If I just remove the red bit, I'm back to where I started. So do you agree with me that I can do this arbitrarily many times. I can put in two of these things as many times as I want, and if I reverse the process, I'm still again back at the original picture. So this is one augmentation rule. Maybe let me just write it down. So I can take a tx can be anything, and I can change it to tx with two ts's, and I've still got the same topological object. But there's something else I can also do. So if I look at this diagram, I can take this arc at the bottom and I can sort of pull it through underneath the rod to the other side. So I've taken a TS and I have changed it into a TC, a different TS, and a TC, right? And if you just undo everything, then you return to your basic loop. So, in fact, if you paid attention, then you'd maybe see that this is basically just a Reidemeister 2 move of the polymer strand relative to the rod. So I've got a strand which is originally separated from the rod, and I pull it across the rod. So obviously you can imagine these boundary conditions slightly differently. The infinitely long rod I could just as well see as though the end at plus infinity is connected to the end at minus infinity. So basically I have two intertwined rings. Topologically this is the same problem. Okay? So this is basically just a Reidemeister 2 move performed on a link of two rings. Anyway, not too important. The bottom line is I've now got a new manipulation rule which tells me if I have a TS, I can replace it by TC, TS, TC. So let's just write that down quickly. TS, and I replace it by TC, TS, TC. Okay, so these are our two manipulation rules for if I start out with some basic configuration that I label with these T's, how can I alter that configuration without changing the topology? Well, I can dress it in all possible combinations of these rules. Now, suppose I want to write down the partition function for this loop. Do you agree with me that all I have to do is I have to sum over all possible combinations of these things? Each one has a weight given by the functional form of the T's, and then I need to integrate all these different combinations, which is a very different process to taking a path integral and having a constraint that just throws out all the ones that I don't want. Here I'm explicitly enumerating the ones that I do want. So suppose I only take this rule. How can I generate all diagrams that belong to this class? Well, I could take Tx, then I can take Tx with Ts squared, then Ts to the fourth, Ts to the sixth, sum all these things, so I get a geometric series. So if I apply this infinitely many times, then what I end up with is my Tx originally and a 1 over 1 minus Ts squared. So this 1 over 1 minus Ts squared is the summation of all possible manipulations like this. So if I sum Ts squared plus Ts fourth plus Ts sixth, etc., I get the summation of a geometric series. This one here, however, has to be applied at each point here. And that's then where it gets difficult to do these two summations together. Okay, so I won't go through that in detail. We then basic, yeah.
Can we get the same Tx if you apply Ts enough times, not even times?
Sorry, 0 times or what?
No, all, like, they have Ts twice. Can you use like 3 times, 5?
Look, the problem is that I need to connect, so let me just maybe go back to the previous picture. The problem is I need to connect this point to that point, which I can't do if I insert an odd number of TS's, right? Because here I'm coming from the bottom, so I again need to come from the bottom when I connect here, which you can't do with an odd number. So that's why only even powers are considered, right? So when I do this summation, I now basically need to do both of these things simultaneously. That's not easy. In fact, we couldn't do it analytically, so we basically found an upper and a lower bound for it. What does that mean? It means that if I have an upper and a lower bound for the partition function, then appropriately I have an upper and lower bound for the free energy. Alright? So basically we then looked at lower bound for this and went and calculated the partition function explicitly. Like I said, the recipe here is I have two augmentation rules. I apply all possible combinations of this, I get some sort of geometric series, and then I just need to integrate over the coordinates. Now what does that look like? There it gets really messy, because suppose I have some diagram in this whole series of valid diagrams. I need to integrate over all x coordinates, all y coordinates, and all arc lengths of these polymer arcs under the constraint that the beginning of the arc must be connected to the end of the arc. That's what these two delta functions give us. And that the sum of the arc lengths together must give us the total length of the polymer. And then this TP is then either a crossing or a same side T. But I have a product of all these things with consecutively joining coordinates. So it's a horrible integral to do. Again, can only be dealt with in some kind of approximation scheme. But we did this, and in the end you get some partition function, and you can find the free energy by just taking the logarithm. Once you have the free energy, you can look at forces by taking derivatives. Hello?
Can you explain the limits?
Sorry, the?
Yeah.
Yeah, okay, good. So, let's take a look here, for instance. The crossing terms, do you agree with me that the y coordinates can take any value? Because I have a strand where I'm considering all possible configurations, like an ideal Gaussian chain, and it's not constrained in the y direction. Do you agree with me? The rod only constrains it in the x direction. So if I do a transformation of coordinates, then I can transform all the x's so that they run from 0 to infinity. So they either run from 0 to infinity or 0 to minus infinity. Because of the rod, right? So all the x coordinates here can either go from 0 to infinity or 0 to minus infinity. So if I just put a minus sign in front of all of these, then I can view it as though all of them run from 0 to infinity. Does that make sense? Okay? The y's can run from minus infinity to plus infinity. Alright? But remember that I have a constraint that the total length of the polymer must still be fixed. So S, I didn't say that, sorry, S is the arc length of each of these loops. So the constraint is all the y integrals run from minus infinity to plus infinity, the x integrals run from 0 to infinity, and the arc lengths can run from 0 to infinity, but I have some minimal cutoff because otherwise things diverge. So this is standard in an ideal chain. You also consider it as a sequence of finite sized steps, right? In the end you take a continuum limit, and that would be then epsilon goes to 0. So technically the x integral, I guess, yeah. This limit is just there because you have a finite step length where at the end you can take a limit that this goes to 0. If you don't do this, then the integrals diverge. So it's reasonably standard that you have some cutoff on a lower length scale in these kinds of problems. So this would basically be the Kuhn length of your polymer, which is basically just the minimal step length that you take with every step in the random loop. So those are the integration domains here. By the x, dy, ds, I just mean all of the x's, all of the y's, all of the s's. Alright? Okay. So once you've done this, you can then calculate the free energy and take derivatives of it to get forces. So we considered this in the case of winding number 1. And then we thought, okay, let's modify this a little bit. So instead of just having it wrap around the rod, let's imagine that I take this polymer and I wrap it through 2 slits. in the plane. So I take the plane, I cut 2 slits here, and now I wrap it through there. So that means the same side terms are constrained to all live in this slit here. And the ones that cross, then obviously have to cross a distance of d. So these 2 slits are a distance of d apart. Okay, so what we did then was, if you confine these things, then obviously you can now take a derivative with respect to certain length scales, and you can get the force that the slits exert on the polymer. And this is what I've shown in this graph. So bear in mind that we've been through quite a number of approximations, some of them really crude. So this might not be a sort of quantitative or quantitatively exact plot, but still it captures some features that are pretty interesting. So suppose I have this picture here, and on the x-axis I've plotted the separation of these 2 slits, and on the y-axis I have the force on the polymer strand from these slits. So if the slits are close together, this force has one sign. As I move them apart, the force changes sign. But this actually makes sense, right? Because if the slits are very close together, you could imagine that if this polymer has a fixed length, then I'm actually compressing it, if the slits are very close together. As I pull them apart, then you'd imagine that the force at some stage will change sign, because then I'm starting to stretch the polymer, right? That's exactly what you see in this plot of the force here. So for us, the surprising thing was that despite the fact that you make a lot of simplifying assumptions here, our model still captures this kind of behavior where you can literally see that different regimes in the forces appear depending on how you confine the polymer, right? So this other plot basically represents the ratio of t's that are on the same side to the number of t's that cross. Okay? And you can see that as you pull the slits further and further apart, so you make d bigger and bigger and bigger, none of these terms occur anymore. Because obviously if I put these slits sufficiently far apart, then the polymer will actually be stretched so far between the slits that none of the polymer strands are still sitting inside the slits. And that's exactly what you see with this ratio decreasing here. So I guess that actually more or less brings me to the end of that example. What I was trying to get across is that when you write down partition functions for these kinds of systems, you can go about it in different ways. You can either sum over everything and have a recipe to throw out the stuff that you don't want, or you can sum over explicitly the things that you do want. Both have advantages and disadvantages. So, like I said, in the context of knots, you can do this through invariants. It's very difficult with those path integrals, and only really basic cases have been solved so far. So, in our approach, we related equivalent configurations instead of just classifying them, right? And then enumerated these things in some combinatoric scheme. You sum all of the diagrams and you get your total partition function. I think if you look back at what Christian talked about and also Mr. Selinger, this is sort of the standard recipe for equilibrium statistical physics. You always want to obtain some free energy, minimize it to get an equation of state, or differentiate it to get forces. So yeah, maybe this just gives a little bit of a different perspective on how exactly can one get to that partition function in the context of topological constraints. Yeah, I think that more or less wraps it up.
So I guess I was just thinking about the x domain and how you limit it from like 0 to infinity or 0 to minus infinity. Don't the number of terms that you care about change depending on which domain you pick, and then wouldn't that affect sort of like the interval term? Or, I guess, I don't know.
So those are two separate questions. So I'm considering all diagrams where I'm looking at all possible combinations of these terms. So I have rules for identifying those diagrams. That's one step. Then, given such a diagram, I can do a coordinate transformation. The reason I can do it is because this t thing is Gaussian. So a transformation of x to minus x still gives me the same weight in a Gaussian. Okay, so it's actually really simple because the weight, you can imagine that the weight that this thing contributes to the partition function is the same. I don't care whether it's on that side or on that side, so its contribution to the partition function is the same. You just have to deal very carefully with the coordinates of the t's that follow each other, because obviously there's always this continuity condition that the beginning of one strand must equal the end of another strand and vice versa. So, but you can deal with that carefully.
So is it those like combinatoric rules that
Precisely.
you have that give you that Gaussian weight, or?
No. The Gaussian weight is what these t's are. So each of these t's is a Gaussian, which tells you what's the probability distribution of a random walk on a half space. So if I have a random walk starting on the surface and ending somewhere else on the surface, this has a Gaussian distribution, which depends on the endpoints. Okay? And now it's these endpoints that I'm integrating over, subject to the constraints that they can't move through the rod.
Okay.
Right. So that's what that's basically. If it's not clear to you, I can show you the calculation. It's really not complicated. It just relies on the fact that x to minus x is a symmetry of the Gaussian. Yes.
So I was just wondering if you could have thought about maybe finding a way to sort of blow up the knot or put a charge on it, and then sort of maybe relaxes to it goes to a ground state that classifies the knot.
So I mean that was what the other part of my thesis work was about. Was suppose I give you some really tangled knot. Can you identify what the underlying prime knot is? And there's some very interesting algorithmic techniques that people have used, which are some of them very closely related to what Greg talked about yesterday. So one idea, for instance, is suppose you have some really tangled, flexible knot. If you give it some bending energy, you'd assume that it maybe pops into a simpler form, right? Another way you could think about it is suppose this thing is like a bicycle tube or a balloon or something. You start pumping it up. Then it would slip, in theory, hopefully, into some configuration that's simpler. Another way you could achieve that is by putting charges along, exactly like you said, along the knot, so that the electrostatic repulsion causes simplification of the knot. So these things have been studied analytically and computationally. And computationally, what they do is they typically have some simulated annealing algorithm. What that means is you have some rule, basically an energy function, which tells you if I change the knot, is this a favorable thing or is it not a favorable thing? If favorable, accept. If not favorable, reject, with some probability. Repeat, repeat, repeat. Now, of course, if you only do this in one direction, so you only ever accept manipulations that simplify the energy or reduce the energy, then these algorithms are quite sensitive to getting stuck in the local minimum. So what they do every now and again is they bounce it out of that by putting in a perturbation that's energetically not favorable. And you can show that the fixed point of those sort of simulated annealing algorithms are then the global minima of this stuff. So people have actually done this in simulations. They take some really complicated knot, try to reduce it, so that in the end you can say on that list of prime knots that I had, which one of them was it. So these ideas have really actually been employed, both analytically and in simulation. Pretty cool stuff. Yeah.
It's really nice. Two things I'm really interested in. One, do you have any kind of sense of how this result compares to the Edwards calculation? I don't quite know how that was done. I have a guess.
So Edwards' paper is confusing, to say the least.
But there's no result that you can compare it to.
His main point was that you can map this whole thing onto a magnetic system, right? Where you basically have an infinitely long solenoid, winding number, then you can write that literally as a gauge theory.
Do perturbation theory.
Exactly. I can't even remember what actual quantities he calculates for this. I actually think maybe he even considers the annealed case where the question is, what distribution of winding numbers would I get?
For fixed field.
Exactly. I don't think he actually calculates physical things, or, sorry, well, quantities like forces or entropic forces.
The entropy is a function of winding numbers.
I think, in fact, most of what Grossbeck at first did was annealed questions, like what is the distribution of winding numbers I would get? And that's an easier question to ask than this quenched scenario where you fix the winding number and you need to sum over a very restricted space of states.
So then the other question, which I think is more compelling to me. So do you have an idea, or can you elaborate on how you might generalize this calculation for a single closed loop?
For a single closed loop.
Right. So not the winding around the rod, but to really to elaborate to construct the ability to generate a knot of a fixed topology by enumerating. I assume you've thought about that, but
yeah.
I had no idea how.
Yeah, so that was basically that was basically the second part of my PhD work,
okay.
Where ideally what you'd want is again maybe some kind of operator that generates equivalent configurations, and then trying to diagonalize this thing in some way. So we tried to look at that.
But could you sort of take that picture and take that loop and connect it at infinity or something to make a knot, to make a single closed loop that you can then do?
I really don't know. What we did do was we tried to take the Reidemeister moves, which relate equivalent configurations, define some sort of stochastic dynamics on that, where the Reidemeister moves give you rules for the crossings. And then sort of through a master equation you try to then ask the question, how do these dynamical topological rules affect the crossings of the knot? So it's not the same question, because here you're trying to enumerate those configurations explicitly, whereas in the dynamical question you're trying to explore, if I have all realizations of these topological rules, what is the likely correlating behavior that you find? So we couldn't do the equilibrium class of calculation for a general knot because it constrains it.
Okay.
So,
Yeah.
Yeah.